A network effect occurs when the value of a product or service to a user rises as more people use it. Think of a telephone. A single phone is useless until there are others to call. Direct same-side network effects. Value grows with the size of the user base on the same side. For example, social media users benefit from more peers. Indirect cross-side network effects. Value on one side depends on the number or quality of participants on the other side. For example, buyers on eBay value more sellers and sellers value more buyers. Two-sided versus multi-sided. Platforms may serve two distinct groups: riders and drivers, or many app store developers, users, advertisers. Economic foundations stem from externalities. Each additional user creates a marginal benefit, a positive externality, for others, shifting the demand curve outward. This creates increasing returns to scale potential for market tipping and explains why platforms often become highly concentrated. Mathematical models give a first-order estimate of how value grows with users. Metcalfe's law direct effect states that the total value V is proportional to the number of possible connections. V approximately K times N minus 1 divided by 2 approximately K times N squared divided by 2, where N is users and K is a constant measuring the value per connection. Example: a messaging app with 10 users can form 45 pairwise chats. With 100 users, 4,950 possible chats, a huge jump. Reed's law extends this to group-forming networks, e.g. Facebook groups. It posits that value grows as V approximately K times 2 to the N because any subset of users can form a sub-network. Though often overstated, it highlights why platforms that enable communities, WhatsApp, Discord, can see explosive perceived value. Indirect effects are captured by a cross-side multiplier function. V sub A equals F of N sub A comma N sub B, where N sub A and N sub B are user counts on each side. A common functional form is V sub A equals alpha times N sub A times N sub B to the beta. Beta measures the strength of the indirect effect. For a ride-hailing app, rider utility rises with more drivers, shorter wait, while driver earnings rise with more riders, more trips. A platform does not become valuable overnight. It must reach critical mass, the smallest user base, where the network effect starts to outweigh costs. The tipping point is the moment the platform's growth becomes self-reinforcing. Mathematically, adoption can be modeled with the logistic S-curve. dN of t over dt equals r times n of t times left parenthesis 1 minus n of t divided by k right parenthesis, where n of t is the number of adopters at time t, r is the intrinsic adoption rate, and k is the market capacity. The inflection point, tipping, occurs at n equals k divided by 2. Before that, growth is slower. After that, it accelerates, then slows as saturation approaches. Another view uses Bass diffusion. F of t equals p times left parenthesis 1 minus n of t divided by m right parenthesis plus q times n of t divided by m times left parenthesis 1 minus n of t divided by m right parenthesis, with p equal to coefficient of innovation, external influence, and q equal to coefficient of imitation, internal network effect. High Q values indicate strong network effects. The platform quickly jumps from early adopters to the mass market once a modest user base is present. Real-world analogy: think of a rooftop concert. A few people gather, critical mass, and the music sounds louder, attracting more listeners. Once the crowd is big enough, the event becomes the talk of the town, tipping. Two-sided platforms often charge different prices to each side to cross-subsidize. Pi equals P sub A minus C sub A times N sub A plus P sub B minus C sub B times N sub B. Because of indirect network effects, a platform may set P sub A low or even 0 to attract a large user base, then charge a higher P sub B to the other side that benefits from the large base. Credit card networks Visa charge merchants a fee high P sub B, while card holders pay no annual fee low P sub A. App stores give developers free entry low P sub A, but take 30% of revenue from sales high P sub B. Dynamic pricing can also be used. Surge pricing in ride-hailing raises rider price when driver supply is scarce, encouraging more drivers to log in, a short-run balancing of the indirect effect. When setting prices, platforms solve a two-stage optimization. First, choose the user base sizes that maximize total surplus given the cross-site externality, then allocate surplus via pricing rules that respect legal and fairness constraints. Because value rises with users, platforms tend to exhibit winner-take-all dynamics. The key drivers are positive feedback loops. More users attract even more users, creating a self-reinforcing cycle. Economies of scale. Marginal cost of adding users is near zero, allowing the leading platform to spread fixed costs over a huge base and lower prices. Strategic lock-in. Data, standards, or APIs become proprietary, making it costly for users to switch. In a multi-sided market, the dominant platform can dictate terms across all sides. For example, Google controlling search users, advertisers, and content publishers. However, winner-take-all is not inevitable. Multi-homing, users using several platforms, and interoperability standards can sustain competition. Real-world case. Airbnb and Booking.com compete despite both having strong network effects, because travelers often browse multiple sites before booking. Multi-homing. Barriers to entry arise when existing platforms make it costly for newcomers or users to leave. Switching costs include data lock-in, for example, a seller's history on Amazon. Learning costs. Users must learn a new UI. Contractual obligations. Long-term advertising contracts. Lock-in can be reinforced by network externalities. Leaving a platform reduces the value of a user's own network. For example, a Facebook user loses friends. Mathematically, the utility loss from switching is delta U equals V old minus V new minus C switch. If delta U greater than 0, rational users stay. New entrants must overcome this by offering superior value, higher V new, or lower switching costs. For example, free migration tools, subsidies. Example, Spotify gave early users playlist import tools to reduce the pain of moving from Apple Music. Because platforms can dominate markets, regulators watch for anti-competitive conduct. Market definition. Should the platform be treated as a single market or as a suite of interconnected markets? Abuse of dominance. Practices like self-preferencing, Google ranking its own services higher, or imposing unfair terms on third-party developers. Merger scrutiny. Combining two platforms with overlapping user bases may create a monopoly. For example, proposed merger of two major ride-hailing firms. Data privacy and platform governance. Rules on how user data can be used, transparency of algorithms, and content moderation standards. Legal frameworks differ. European Union Digital Markets Act, United States antitrust lawsuits, but share the goal of preserving fair competition while allowing innovation. Platforms often adopt compliance programs, independent audits, open APIs, and fair play policies to reduce regulatory risk. To evaluate a platform, managers use a mix of financial and non-financial key performance indicators. Core metrics include gross merchandise volume, GMV, total transaction value flowing through the platform, for example, eBay's GMV. Take rate, percentage of GMV retained as revenue, reflects pricing power. Network size, active users on each side, daily active users, monthly active users. Engagement, average sessions per user, time spent, repeat rate. Cross-site elasticity, change in side activity per unit, change in side B size, measured via regression, delta log QA divided by delta log NB. Contribution margin, revenue minus variable costs, important because fixed costs are sunk and scale-driven. A strategic evaluation framework combines external analysis, industry network effect intensity, entry barriers. Internal analysis, platform architecture, data assets, governance. Scenario modeling, impact of reaching critical mass, effects of a price change on each side. Dashboard tracks leading indicators, user acquisition cost, churn, activation rate, alongside lagging indicators, GMV, profit. Numerical Metcalfe calculation. Question: a new professional networking platform has 5,000 users. Assuming Metcalfe's law with K equals $0.01 per connection, estimate the total network value. If the platform doubles its user base, what is the percentage increase in value? Solution outline. Value with 5,000 users. V1 equals 0.01 times 5,000 times 4,999 divided by 2 approximately equals 0.01 times 12,497,500 equals $124,975. With 10,000 users, V2 equals 0.01 times 10,000 times 9,999 divided by 2 equals 0.01 times 49,995,000 equals $499,950. Percentage increase. Open parenthesis V2 minus V1 close parenthesis divided by V1 times 100 approximately equals open parenthesis 499,950 minus 124,975 close parenthesis divided by 124,975 times 100 approximately equals 300%. Two-sided pricing. Question: an online marketplace charges sellers a 10% commission and offers buyers free access. Each seller generates on average $200 in sales per month, and the platform has 1,000 sellers and 20,000 buyers. Compute monthly profit ignoring other costs. If the platform decides to charge buyers a $1 subscription and reduces seller commission to 8%, what profit change results? Solution outline. Original profit equals commission rate times average sales times number of sellers equals 0.1 times 200 times 1,000 equals $20,000. New profit, seller commission revenue equals 0.08 times 200 times 1,000 equals $16,000. Buyer revenue equals $1 times 20,000 equals $20,000. Total equals $36,000. Profit increase equals new profit minus original profit equals 36,000 minus 20,000 equals $16,000. Critical mass logistic model. Question: adoption follows dn over dt equals 0.3n times open parenthesis 1 minus n over 10,000 close parenthesis. Solve for n of t given n of 0 equals 100 and compute n at t equals 12 months. Solution outline. Logistic solution. N of t equals k divided by open parenthesis 1 plus open parenthesis open bracket k minus n0 divided by n0 close bracket closed parenthesis e to the minus rt close parenthesis. With k equals 10,000, r equals 0.3, n0 equals 100. Compute open parenthesis k minus n0 close parenthesis divided by n0 equals 9,900 divided by 100 equals 99. Then n of 12 equals 10,000 divided by open parenthesis 1 plus 99e to the minus 0.3 times 12 close parenthesis. Exponent term e to the minus 3.6 approximately equals 0.0273. Multiply 99 by 0.0273 approximately equals 2.70. Denominator approximately equals 1 plus 2.70 equals 3.70. N of 12 approximately equals 10,000 divided by 3.70 approximately equals 2,703 users. Network externality elasticity. Question: in a ride-hailing platform, rider demand Q sub R equals 5,000 minus 20 P sub R plus 0.5 N sub D, where P sub R is rider price in dollars and N sub D is number of drivers. If price is $5 and there are 1,000 drivers, compute rider demand and the elasticity of rider demand with respect to driver count. Solution outline. Plug values. QR equals 5,000 minus 20 times 5 plus 0.5 times 1,000 equals 5,000 minus 100 plus 500 equals 5,400 rides. Elasticity epsilon equals partial QR over partial ND times ND divided by QR equals 0.5 times 1,000 divided by 5,400 approximately equals 0.093. These questions test definition, quantitative modeling, and strategic pricing under network effects.